Chapter 5. Error Analysis. 5.01 Significant Figures. The significant figures express the accuracy with which a physical quantity may be expressed. The digits, whose values are accurately known in a particular measurement, are called its significant figures. Greater the number of significant figures obtained when making a measurement, more accurate is the measurement. Conversely, a measurement made to only a few significant figures is not a very accurate one. For example, a recorded figure of 1.21 means the quantity can be relied on as accurate to 3 significant figures, and a figure of 1.212 is said to be accurate to 4 significant figures. Thus, significant figures in a measured quantity indicate the number of digits in which we have confidence. In the example given above, one can easily find the number of significant figures. It is because each digit used to express the magnitude of the measurement was significant. However, when we use the different systems of notation, this is not always the case. Suppose that we write the average distance s from the Earth to the Moon as s equals 377,000 km equals 3.77 into 10 power 5 km. Does this number have 6 significant figures? No, this measurement is given to an accuracy of only 3 significant figures. The 3, the 7, and the 7 are significant. The last 3 zeros merely indicate the correct location of the decimal point. Similarly, 0.000123 centimeters contains only 3 significant figures. The zeros which merely locate a decimal point are not significant figures. The following rules have been set up for determining the number of significant figures. 1. All non-zero digits are significant. 15,248 contains 5 significant figures. 2. All zeros occurring between 2 non-zero digits are significant. 108.006 inv contains 6 significant figures. 3. All zeros to the right of a decimal point and to the left of a non-zero digit sign are never significant. 0.00967 contains 3 significant figures. The single zero conventionally placed to the left of the decimal point in such an expression is also never significant. 4. All zeros to the right of a decimal point are significant, if they are not followed by a non-zero digit. 30.00 contains 4 significant figures. B. All zeros to the right of the last non-zero digit after the decimal point are of significant. 0.07800 contains 4 significant figures. 5. All zeros to the right of the last, rightmost, non-zero digit are not significant. 2020 contains 3 significant figures. B. All zeros to the right of the last non-zero digit are significant, if they come from a measurement. Suppose that the distance between 2 objects is measured to be 2020 meter, to the nearest meter. Then, 2020 meter contains 4 significant figures. This distance can be expressed as 202,000 centimeters or 2.02 kilometer. So that significant figures still remain 4, irrespective of the way of expressing the measurement. The distance should be expressed as 2.020 x 103 m or 2.020 x 105 centimeters or 2.020 kilometers. Problem 5.01. Solution. 1. 6,729 Newton has 4 significant figures. Rule 1. 2. 0.024 centimeter has 2 significant figures. Rule 3. 3. 6.0023 gram per centimeter cube has 5 significant figures. Rule 2. 4. 2.520 into 10 power 7 meter has 4 significant figures. Rule 5. B. V. 0.08240 Newton per meter square has 4 significant figures. Rule 4. B. 6. 4,200 has 2 significant figures. Rule 5. A. 7. 4.57 into 10 power 8 has 3 significant figures. Rule 5. B. 8. 91.000 has 5 significant figures. Rule 4. A. 5.02 rounding off to desired number of significant figures. A number is rounded off to the desired number of significant figures by dropping 1 or more digits to the right. When the first digit dropped is less than 5, the last digit retained should remain unchanged, and when it is 5 or more, 1 is added to the last digit retained. 5.03 Significant figures in calculations. In an experiment, usually a number of measurements are made, and to obtain the result, they are, then, compounded, i.e. added, subtracted, multiplied, or divided. If all the observations have been made with great accuracy except one observation, then the inaccuracy in the single observation is going to mark the result adversely. To understand this point, consider a strong iron chain of which one link is weak. Obviously, the chain cannot be stronger than its weakest link. Actually, it forms the basis of compounding the measurements and then to know the number of significant figures. 5.04 Significant figures in addition and subtraction. The accuracy of a sum or a difference is limited to the accuracy of the least accurate observation in the addition and subtraction rule. Do not retain a greater number of decimal places in a result computed from addition and / or subtraction than in the observation, which has the fewest decimal places. Illustration 1. Add and subtract 428.5 and 17.23 with due regards to significant figures. If we add 428.5 and 17.23, the sum is 445.73, and subtract 17.23 from 428.5, then the difference equals 411.27. But in physics, the sum and difference taken in this manner are discouraged. In fact, in the data 428.5, we have assumed 0 to be in second place after decimal. The data 428.5 might have been written to first decimal only, because of the inability of the instrument to measure it to the further accuracy. Therefore, the choice of 0 only in the second decimal place of the data is not justified. To add or subtract in such a situation, there are two methods. 1. By rounding off the answer. The data 428.5 is the weakest link as its value is known up to first decimal only. Therefore, the answer should also be retained only up to first decimal place. As said earlier, in case the second decimal is occupied by 5 or more than 5, the number in first decimal is increased by 1. On the other hand, if the second decimal is occupied by a number less than 5, it is ignored. Rounding off the results of the above sum and difference to the first decimal, we have correct sum equals 445.7 and correct difference equals 411.3. 2. By rounding off the other data. The result can also be obtained by rounding off the other data in accordance with the data, which is the weakest link. The data 17.23 should be rounded off to 17.23 in second decimal place is ignored, and then added to or subtracted from 428.5. Thus, we have correct sum equals 445.7 and correct difference equals 411.3. Hence, 428.3 plus 17.23 equals 445.7 and 428.5 minus 17.23 equals 411.3. 5.05 Significant figures in multiplication and division. When the values of different observations are multiplied or divided, the number of digits to be retained in the answer depends upon the number of significant figures in the weakest link. Rule. Do not retain a greater number of figures in a result computed, multiplication and / or division than the least number of significant figures in the data from which the result is computed. Illustration 2. Multiply 312.65 and 26.4 with due regards to significant figures. If we multiplied 312.65 by 26.4, the answer is 8253.960. But as the weakest link, i.e. the data 26.4 has only 3 significant figures, the correct result of multiplication will be 8250. This is because in 8250, there are 3 significant figures. Hence, 312.65 into 26.4 equals 8250. Illustration 3. Divide 2.5 into 10 power 5 by 4.75 into 10 power 3 with due regards to significant figures. The answer is 52.6316. Since the weakest link 2.5 into 10 power 5 has only 2 significant figures, the correct result of the division will be 53. Hence, we have 2.5 into 10 power 5 divided by 4.75 into 10 power 3 equals 53. 5.06 Theory of errors, precision of measurement. Foundation of a science, particularly of physics, is experiment. In physics, the discovery of a new law or principle is acceptable only when the experiment approves it. In order to get as close to the truth as possible, physicists have not only been trying to design more and more perfect instruments but have also developed a theory of errors, which helps in eliminating possible errors in the observations. The theory of error originates from the following two assumptions: 1. That every observer performing an experiment is careless to some extent and is thus liable to commit mistake. 2. That every instrument used in an experiment is defective to some extent. Hence, the observation made with an instrument has got some inherent error. In fact, errors and mistakes are two separate things. The term mistake is used to denote a gross error. It can be avoided by care on the part of the experimenter and should be avoided as the result cannot be corrected for them. On the other hand, the uncertainty in a measurement is called an error. It tells the limits within which the true value may lie. 5.07 Error of measurements. There is only a limit up to which measurements can be made with a given measuring instrument. This limit is called the least count of the instrument. For example, a meter rod can measure length accurately up to 0.1 centimeters, whereas a vernier calipers can measure length accurately up to 0.01 centimeters. However, when we make use of various measuring instruments, various types of errors creep into the observations. There can be the following possible types of errors in measurements. 1. Constant error. When the result of a series of observations are in error by the same amount, the error is said to be a constant one. For example, in measuring the length of a cylinder by a vernier calipers whose graduations are faulty, say 1 cm on the scale is actually 0.9 cm, the measured length will always be greater than the true value by a constant amount. In order to avoid constant error, the measurements are made by as many different methods as possible. 2. Systematic error. A systematic error is one that always produces an error of the same sign. These are due to known causes. This type of error is eliminated by detecting the source of the error and the rule governing this error. Systematic error may be subdivided into the following types. 1. Instrumental errors. These are inherent errors of the apparatus and the measuring instruments used. A simple example is the zero error of a measuring instrument. All instrumental errors come under this category. The instrumental error, if any, can be detected by interchanging two similar instruments or by using different methods for measuring the same physical quantity. 2. Observational or personal errors. The errors due to the personal peculiarities of the experimenter are known as personal errors. For example, parallax error while reading the positions of uprights on the optical bench. The more experienced the experimenter is, the lesser it is. These errors can be minimized by obtaining several readings carefully and then taking their arithmetical mean. 3. Errors due to external causes. These errors are caused by external conditions, pressure, temperature, wind, etc. For example, expansion of a scale due to increase in temperature. These errors can be taken care of by applying suitable corrections. 4. Errors due to imperfection. Sometimes, even when we know the nature of the error, it cannot be eliminated due to imperfection in experimental arrangement. For example, in calorimetry, loss of heat due to radiation, the effect on weighing due to buoyancy of air, etc. These errors will always exist but observations can be corrected for them. 3. Random errors. These errors are due to unknown causes and are sometimes termed as chance errors. In an experiment, even the same person repeating an observation may get different reading every time. For example, measuring diameter of a wire with a screw gauge, one may get different readings in different observations. It may happen due to many reasons. For example, due to non-uniform area of cross-section of the wire at different places, the screw might have been tightened unevenly in the different observations, etc. In such a case, it may not be possible to indicate which observation is most accurate. However, if we repeat the observation a number of times, the arithmetical mean of all the readings is found to be most accurate or very close to the most accurate reading for that observation. That is why, in an experiment, it is recommended to repeat an observation a number of times and then to take their arithmetical mean. 5.08 Gross errors, or mistakes. These are the results of sheer carelessness on the part of experimenter. No correction can be applied for them and hence must be avoided by exercising due care. They are of the following types. 1. Neglect of the sources of error. This type of gross error results due to negligence towards sources of errors. For example, for plotting the field of a magnet, improper setting of the magnet along n.s line, presence of magnetic material in the vicinity of the magnet, etc. 2. Reading the instrument incorrectly. Sometimes, over a meter scale, 1 cm is divided in 20 parts instead of 10 parts, or in a voltmeter or ammeter, 1 volt or 1 ampere might have been divided in 20 or 5 parts instead of 10. The experimenter may read the instrument without paying due attention to the value of 1 division. 3. Improper recording of the reading. This type of mistake is committed by the experimenter when he records the reading wrongly. For example, he may record 21.3 in place of 23.1. It happens in undue haste or when the experimenter mentally carries the reading for a long time. 5.09 Absolute, relative and percentage error. Absolute error. The difference of the true value, standard value, and the experimental value, observed value, of a physical quantity is called absolute error. It is expressed in the units of measured quantity. Therefore, absolute error equals true value minus experimental value. Suppose in an experiment on determining the value of acceleration due to gravity, the value comes out to be 945 centimeter per second square. We know that the value of the acceleration due to gravity is generally taken as 980 centimeter per second square. Therefore, absolute error in the value of acceleration due to gravity equals 980 minus 945 equals 35 centimeter per second square. Relative error. The knowledge of the relative error is more important than that of the absolute error in a measurement. The relative error is defined as the ratio of the absolute error to the true value. Therefore, it has no units. Therefore, in the above example, the relative error in the value of acceleration due to gravity equals 35 by 980 equals 0.36. Percentage error. The relative error expressed as percentage is known as the percentage error. Therefore, in the above example, the percentage error in the value of acceleration due to gravity equals 35 by 980 into 100 equals 3.6%. Problem 5.02. The length and breadth of a rectangular object area 25.2 cm and 16.8 cm respectively and have been to formula measured to an accuracy of 0.1 cm. Find the percentage error in the area of the object. Solution. Now, area, A equals length into breadth percentage error in area equals percentage error in length, plus, percentage error in breadth, equals 0.1 by 25.2 into 100, plus, 0.1 by 16.8 into 100, equals 0.4% plus 0.6% equals 1.0%. 5.10. Permissible error in a result. Even when an experimenter has managed to avoid gross error by exercising due care and the instrumental errors have been avoided by selecting a perfect apparatus for the experiment, still another type of error may creep in the result of an experiment. It is due to the limits put on the measuring abilities of various kinds of instruments used, while performing the experiment owing to their least counts. Such an error is called the permissible error. For example, suppose that the temperature a liquid is read at 25.4 degrees Celsius on a thermometer calibrated in degrees. If the reading is estimated to the nearest 0.1 degrees Celsius, the temperature should be recorded as 25.4 plus or minus 0.1 degrees Celsius. This is the scientific way of recording a reading with the limits of error. In the present case, the temperature of liquid will be in the range 25.3 degrees Celsius to 25.5 degrees Celsius. Similarly, if the length of an object is read as 34.7 cm with a meter rod calibrated in centimeter and correct to the nearest 0.1 cm, then the length of the object should be recorded as 34.7 plus or minus 0.1 cm. 5.11. Propagation of error. The final result of an experiment is calculated from a formula from the number of observations for the various quantities taken with the help of different instruments. As we shall see, each of these observed quantities does not influence the result to the same extent. Some observation may influence the result more than what the other does. We shall now calculate the maximum permissible error in different cases. 1. When the result involves the sum of two observed quantities. 2. When the result involves the difference of two observed quantities. 3. When the result involves the product of two observed quantities. 4. When the result involves the quotient of two observed quantities. 5. When the result involves the product of the powers of observed quantities.